Now we're going to spend a bit of time talking about C4, C3, and CAM photosynthetic pathways. You don't need to memorize all of the enzymes involved in the reaction, i.e. there's more detail behind this. And I've linked two videos as well. One's like super basic and the other one is a bit higher level than we want, but I think it shows the mechanisms well. But you should know the adaptive advantages and be able to kind of compare and contrast C3, C4, and CAM. So C4 is a photosynthetic pathway that reduces photorespiration and involved independently several times. It involves biogeochemical and morphological specialization. Many grasses use this: corn, sugarcane, sorghum, and also edicots. There we go. So C4 is generally like a lot of our grasses. Again, corn's a big C4 plant. In C4 plants, carbon dioxide uptake and the Calvin-Benson cycle occur in different parts of the leaf. So what we're doing is we're moving the carbon dioxide uptake away from the Calvin-Benson cycle, the carbon dioxide fixation part. Carbon dioxide is taken up by mesophyll cells in a PEP case, which has a greater affinity for carbon dioxide than Rubisco, and it does not have oxygenase affinity. The carbon dioxide becomes part of a 4-carbon compound, hence the C4. The 4-carbon compound is transported to the bundle sheath where carbon dioxide is released, and the Calvin cell is the Calvin-Benson cycle is operating. High carbon dioxide in the bundle sheath releases oxygen uptake by Rubisco. So what this looks like at the kind of cellular level is carbon dioxide is coming in through the stomate, and instead of going directly in where the Calvin cycle is operating, it goes into this PEP case where the PEP case is able to hold a lot of carbon dioxide, and then it kind of aliquots that out or releases it to the Calvin-Benson cycle. So this allows the plants to open up the stomate, say at night or when temperatures are cooler, bring in a fair amount of carbon dioxide without losing a lot of water through transpiration, and then the Calvin-Benson cycle can operate and not have that leak of water. More ATP is required for the C4 pathway, but it gives greater photosynthetic efficiency and gives these plants an advantage over C3 plants in high temperatures. So it's not as efficient, but it is the only way to go in really high temperatures where water is limiting. The water use efficiency is the transpiration losses are minimized because the PEP case can take up CO2 when the stomates are not fully open as well. So it's more water efficient. It operates better at higher temperatures, but in a more moderate climate, C3 plants tend to do better. This is an interesting graph looking at the average July minimum temperature and then the percentage of C4 plants in the regional grass floras. And so if your July minimum temperature, which is kind of like the minimum temperature of the year, is quite high, you have almost entirely C4 plants, where if that July minimum temperature is quite low, you tend to be dominated by C3 plants. There's also the crassulin acid metabolism, CAM. And CAM minimizes water loss by opening the stomates at night when it's cooler and humidity is higher, and then close them during the day. So I misspoke a little bit earlier, but stomates in C4 can be partially open and bring in carbon dioxide, where CAM really separates the day and night. And so at night the stomates open and allow carbon dioxide in. At night, CAM plants uptake CO2 using a PEP case and make a 4-carbon organic acid and store it in vacuoles. During the day, the molecule is broken down to a supply of carbon dioxide for the Calvin-Benson cycle, and high carbon dioxide concentrations reduce photorespiration. Cam plants are often succulent, so you can think of this as succulents. Anything that has a thick, waxy, or fleshy stems or leaves, common in arid or saline environments. So here the stomate opens at night. Carbon dioxide comes in to the PEP case, stored in this vacuole of C4 organic acid. And then during the day when the stomate's closed, that organic acid is brought over to the Calvin cycle, where it's converted into starches. Here's some examples of succulents. Some cam plants occur in the humid tropics. Most epiphytes that grow in tree branches have less access to water. So even if there's a fair amount of humidity, you might not be able to have your roots in the ground to absorb water. Cam is also found in aquatic plants such as quillwort, and the uptake of carbon dioxide diffusion into water is slow. Cam can facilitate carbon dioxide uptake in low carbon dioxide concentrations of the aquatic environment. So in general, because of gas diffusion in water, there's generally a lower concentration of carbon dioxide in the water compared to the land. Some plants can switch between C3 and CAM, facultative CAM. When water is abundant, they use the sort of more efficient C3 pathways, which allows it to gain more carbon. And if conditions become arid or saline, they switch to CAM. It's irreversible in some species, but not in others. So here's kind of a brief overview of C3, C4, and CAM, where C3 carbon dioxide is coming directly into the Calvin cycle. In C4, there's a mesophyll cell that's bringing in carbon dioxide, storing that as typically a C4 acid, bringing that over in the Calvin cycle, where the carbon dioxide is producing sugars. And then in the CAM cycle, there's usually a vacuole involved, where C3 and C4 carbon's fixed in an acid, and that's then released to the Calvin cycle. The big difference with CAM is the day and night cycle. So that's just a very quick overview based on the book. There's 2 videos posted I encourage you to look at. One, again, is much more basic, and the other one is more detailed about the enzyme pathways. The big thing is to understand the physiology, what's happening when are stomata open, things like that. When is a mesophyll cell involved? The kind of big components of the differences between C3 and C4, and when they have adaptive advantages.